Hello learners, my name is Mr. Poch Lola. Let me welcome you to Black Slides, a platform where you come and learn for free if you are a candidate, Msce candidate, or if you are doing a different curriculum such as IGCSE of the University of Cambridge. You are most welcome. You are most welcome to this platform. You are going to find something useful pertaining to your syllabus. For the time being, I decided to make this video for Msce candidates in a subject called physics and in particular in a topic called digital electronics, and this happens to be lesson number 2. Recall that in lesson number 1 of the topic digital electronics, we looked at the band theory, what the band theory is, and just a quick reminder, we mentioned that the band theory states that when the two atoms are brought closer to each other, their energy levels split or divide up into smaller energy levels. Those smaller energy levels are what we call bands. And we went on to say that in digital electronics there are 2 types of bands, namely the valence band and the conduction band. Alright, and for any material to conduct electricity, there must be electrons in the conduction band. So naturally, the conduction band does not have electrons. Alright, it's empty. Naturally, the conduction band is empty. So electrons should migrate, should jump from the valence band through a gap which is called the forbidden gap to the conduction band, where the electrons will be available for conduction. If this doesn't happen, then such a material will not conduct electricity. Alright, we also looked at a classification of materials based on their ability to conduct electricity. Namely, we looked at insulators, which hardly conduct electricity. Alright, we said that insulators don't conduct electricity just because there is a wide gap, very large gap between the valence band and the conduction band. So electrons find it hard to jump from the valence band to the conduction band. So this makes electrons absent in the conduction band, hence insulators do not conduct electricity. We also looked at another class of materials which we call semiconductors. You recall that semiconductors are materials whose conductivity lies between insulators and conductors. And examples of semiconductors include silicon and germanium. Remember, silicon and germanium belong to the same group in the periodic table, which is group number 4. Okay, and the semiconductors are capable of conducting electricity simply because their forbidden gap is smaller compared to the forbidden gap in insulators. So electrons can easily jump from the valence band to the conduction band. Hence, semiconductors conduct electricity, although partially. And we saw that conductivity of semiconductors can be enhanced by simply raising the temperature of the semiconductors, all right, which causes electrons to gain kinetic energy and hence jump from the valence band to the conduction band. Unlike insulators, even if you heat insulators such as plastics, the electrons cannot jump from the valence band to the conduction band. Just before that happens, the material will be bent completely. All right. Okay. We looked at conductors exemplified by all metals such as copper, zinc, silver, iron, and other metals. Unlike semiconductors and insulators, conductors do not have a forbidden gap. In other words, the valence band and the conduction band in conductors overlap with each other, which makes it very easy for electrons to move from the valence band to the conduction band. Hence, metals conduct electricity very, very easily. All right. And we pointed out that heating a metal or conductor does not in any way enhance or increase conductivity. Instead, it reduces conductivity. Heating a conductor will reduce the conductivity of metals. Okay, simply because when a metal is heated, it is going to cause particles, stationary particles such as atoms, to vibrate. Okay, so as the atoms vibrate, they are going to interfere with the flow of electrons from the valence band to the conduction band. Recall that temperature affects the conductivity of metals due to increased resistance. So when the metals are heated, their resistance increases and the current flowing through them decreases. Therefore, heating a metal or a conductor decreases the conductivity. In case they ask in an exam, why does the conductivity of metals or conductors decrease when the temperature is raised? It's because raising the temperature of conductors would increase the resistance of the conductors. All right, so that resistance would reduce the current flowing through the materials. So that's what we discussed in lesson number 1. Welcome to lesson number 2. My name once again is Mr. Pochilola. In case you want to book private tuition, don't hesitate to contact us on the number shown on this screen. We'll be very quick and prompt to come back to you and arrange lessons for you. All right, like I've always said, and I'd like to say now that you do yourself some good by liking our channel, this channel, and also considering to subscribe as well as to hit the notification bell so that each time we upload a new video, you are the first ones to know and access your lessons. All right, so once again, do yourself that favor, and in the process you're also doing us a similar favor. All right, so welcome to today's lesson. In today's lesson, we are going to be looking at the 2 types of semiconductors. 2 types of semiconductors. You remember semiconductors, by semiconductors we are referring to elements such as silicon and the germanium. All right, so semiconductors can be classified into what we call intrinsic and extrinsic semiconductors. Take note that we have two types of semiconductors, namely intrinsic and extrinsic semiconductors. So we are going to discuss what each one of them is, right? Starting off with intrinsic semiconductors. So what are intrinsic semiconductors? Definition. We define an intrinsic semiconductor as a pure semiconductor whose electrical conductivity is enhanced by temperature alone. Okay, for example, silicon and the germanium. In lesson 1, I pointed out that you can increase the conductivity of semiconductors by heating or by raising their temperature, right? So when temperature is raised, the electrons gain kinetic energy, enabling them to jump from the valence band to the conduction band. All right, so if semiconductors can be improved, or if the electrical conductivity of semiconductors can be improved by temperature alone, then such semiconductors are called intrinsic semiconductors. And their nature is that they are pure elements, okay? It's pure silicon and pure germanium, right? So recall from what we said last time that assuming the electron is here initially, and we apply heat at some point on the material, the electrons will become excited, they'll move, they'll gain kinetic energy and jump from there and then to another place, and then finally cross the small forbidden gap to the conduction band where the electrons will be available for conduction. All right. So what you need to understand is that at the room temperature, these elements do not conduct. In other words, they behave like insulators, right? It is only when the material is heated that electrons will gain thermal energy or heat energy, right, which translates into gain in kinetic energy, which is the energy of movement. All right, so this will cause them to move from the valence band from here, all right, or through the small forbidden gap to the conduction band. All right, so we are saying when an extrinsic semiconductor is heated, the electrons gain thermal energy or heat energy, which essentially also leads to gain in kinetic energy, and they'll move from the valence band to the conduction band. Right, so the conduction in intrinsic semiconductors is due to electrons and the holes which are left behind by the excited electrons, which jumped from the valence band to the conduction band. All right, so take note, we are saying that when an electron leaves a spot, let's say initially the electron is here, all right, so when it jumps to another place, the original place becomes positively charged. Positively charged. Okay, there's what we call a hole left. Right, so that positive charge or positive charge carrier is called a hole. Right. So when it moves to another place, the new place also becomes a hole when the electron jumps like that to another place, and so on. So here we have 3 holes. It doesn't mean that there were 3 electrons were moved from each place. No, the original place was here. The original location of the electron was here where I'm pointing. All right, so it moved from there to a new place, making this original point positively charged. Similarly, when it leaves this new place, it is also going to leave a positive charge there, and so on and so forth. So we are saying the conduction in these materials is largely due to 2 types of charge carriers. There are electrons which are negatively charged, and the holes which are positively charged. Please take note that holes are not protons. Although they are positively charged, they are not protons. They are they just resemble protons, which are also positively charged. So that's what we are saying there in terms of the two types of semiconductors. All right. So one type of semiconductor, like we said, is intrinsic semiconductors, whose conductivity can be increased by simply raising their temperature. All right. So how does temperature do that? It is due to what? When electrons are heated, when the material is heated, the electrons gain kinetic energy and cause them to jump from the valence band to conduction band, where they will be available for conduction. All right. So in case you have questions on intrinsic semiconductors, don't hesitate to come back to us to comment, to present your question in the form of comment in the comment section below, or you can send us a text message on the number that we provided earlier on. My name once again is Mr. Chilola. All right. Another type of semiconductors, remember we are looking at the types of semiconductors, is what is called extrinsic semiconductors. The first type we looked at in the previous slide is intrinsic semiconductors. All right, so intrinsic semiconductors are those whose conductivity can be increased by simply raising their temperature, and we have two examples, namely silicon and germanium. All right, what about extrinsic semiconductors? So the opposite of intrinsic is extrinsic. All right, so an extrinsic semiconductor is an impure semiconductor made by adding impurities to an intrinsic, which is pure semiconductor, all right, by a process called doping. All right. So we are saying an extrinsic semiconductor is an impure semiconductor, okay, made by adding impurities to an intrinsic semiconductor through a process called doping. So what are we saying? We are saying that when you take a pure semiconductor such as silicon, add a little bit of impurities to it, we shall soon see what those impurities are. The result is going to be the formation of extrinsic semiconductors. All right. So take note that extrinsic semiconductor is impure. All right. This, what makes it impure is an addition of some kind of elements, small amounts of certain elements which we are going to unveil shortly. All right, so please take note of the definition and differentiate this definition from that of intrinsic semiconductor. So an extrinsic semiconductor is an impure semiconductor made by adding impurities to an intrinsic semiconductor. Please take note that each time we mention intrinsic semiconductor, we are referring to pure elements such as silicon and germanium. So the process by which extrinsic semiconductors are made from intrinsic semiconductors is called doping. Okay, which is defined as follows. Doping is defined as the process of adding minute impurities to an intrinsic, which is pure semiconductor, to enhance the electrical conductivity. All right, so the reason why we dope or we add impurities to a pure semiconductor, intrinsic semiconductor, is to increase or improve the electrical conductivity of the semiconductor. Please take note of the definition of doping. The examiner will simply ask you define the term doping in relation to semiconductors. You have to say that It is a process of adding minute. Minute means very small quantities, all right? So doping is defined as the process of adding minute or very small quantities of impurities to a pure semiconductor in order to increase its electrical conductivity. All right. Okay, so we've seen what extrinsic semiconductors are, and we're saying that they're made by a process called doping, which we have defined as the process of adding minute impurities to an intrinsic semiconductor. Right? Examples of intrinsic semiconductors are silicon and germanium. So you add a little bit of some element, which we are going to discover shortly, and the result will be the formation of an extrinsic semiconductor. Remember, ideally we are saying that intrinsic semiconductors are doped in order to improve their electrical conductivity. All right, so how is the doping process done? Okay, so we are going to look at the doping process. Please pay attention. This is one of the mostly examined area in paper 1 of your physics, Msce physics. Okay, so they'll ask you to define doping or define extrinsic semiconductors or differentiate between extrinsic semiconductors and intrinsic semiconductors, so please pay attention. All right, so doping in semiconductors results into two types of extrinsic semiconductors. Okay, so we are saying when a pure semiconductor is doped, you can either produce an N-type extrinsic semiconductor or a P-type extrinsic semiconductor. N here means negative type, and P is positive type. So we are saying doping can produce either negative type extrinsic semiconductor or positive type extrinsic semiconductor. Please take note of that. So how is each produced? So we are going to look at how doping can make a particular extrinsic semiconductor negative and another one positive. Okay, so the examiners will simply ask you explain how an N-type extrinsic semiconductor is formed, or explain how a P-type extrinsic semiconductor is formed. So listen, pay attention to the explanation as we look at the next slide. My name once again is Mr. Chilola, and I appreciate the fact that you are there learning. Okay, it is your learning that encourages us to produce more videos for you. All right, so thank you very much. Keep watching. All right, so we are looking at these two types of extrinsic semiconductors. We're saying we have N-type and the P-type. So how is each produced? That's what we'll have to talk about next. Remember to like, subscribe, and hit the notification bell so that you don't skip any videos as they are being uploaded. All right, so we are looking at how an N-type extrinsic semiconductor can be made by a process called doping. Take note, you have a 2 marks question that asks you to explain how an N-type extrinsic semiconductor is formed. Remember that the formation of extrinsic semiconductors is done by a process called doping. All right, so N-type extrinsic semiconductors are formed by adding a pure semiconductor, which is a group 4 element. An example of a group 4 element is silicon, all right, with a pentavalent element or atom. Penta, recall penta means 5, Valent means electrons. Alright, and mostly this is group number 5 elements. Take note. We are saying an N-type, in order to make a semiconductor negative, you need to add a group 5 element to a pure semiconductor, which is either silicon or germanium. All right. So what are we saying? We are saying that an N-type extrinsic semiconductor is formed by doping or adding a pure semiconductor such as silicon or germanium with a pentavalent. Pentavalent atom is one which is in group number 5. The pure semiconductor is any element in group number 4, and the doping element is an element from group number 5. Examples of these doping atoms are phosphorus, antimony, and arsenic. If you go to your periodic table, the full periodic table, which has 119 elements, just go to group number 5 of the periodic table, you find these elements there. These are called doping elements. They make a pure semiconductor such as silicon and the germanium to become any type, or to have a negative terminal, so to call it. All right. So a pure semiconductor such as germanium has 4 electrons available for formation of a covalent bond with 4 neighboring atoms. Okay, so let's look at this in relation to the diagram we have here. If you look at this structure, this is a covalent structure of it's a giant structure, or sometimes it is called, of germanium. Okay, so you have germanium atoms all around. You have germanium atoms, except the one which is in the middle. This one here, this is phosphorus, which is to be added to the structure of germanium. Okay, so in this case, the phosphorus is a doping element. So when a group 5 impurity, such as phosphorus, is added, 4 of its 5 electrons participate in the bonding, but 1 electron has no place to form a bond. Listen very carefully there. This is what we are saying. We are saying that when you place phosphorus here, okay, phosphorus belongs to group number 5 of the periodic table. So because of that, it has 5 electrons in its outer shell. Okay. So when being added to germanium has 4 bonds. It has 4 bonds. Each germanium atom has 4 bonds. We have 1, 2, 3, 4. 1, 2, 3, 4, and so on. So during bonding, phosphorus, which has 5 electrons in its outer shell, will only have its 4 electrons bonded to 4 different germanium atoms. Okay, so for example, you have this electron from phosphorus bonding to an electron, again germanium, this germanium here, and this electron here bonds to this germanium this side, this electron there bonds to this germanium atom down here, and finally this electron bonds to this germanium to the right, to the left, and the 1 electron remains unbonded, which is free electron. All right, so the remaining electron is donated for electrical conductivity. So this electron which is not bonded is going to be free. is going to be available for conductivity. So in this case, phosphorus is considered to be a donor atom. It is donating its electron for conductivity. The first 4 electrons are bonded, fully bonded, okay, to germanium atoms, and the 5th electron remains unbonded. So this electron which remains unbonded is going to be free, it's going to be available for conduction. And since this electron is coming from phosphorus, the doping element, the electron will make phosphorus a donor atom. So the resulting semiconductor is now called an N-type semiconductor, where N stands for negative charge carrier, okay, resembling an electron. Actually, this is an electron. So the electron, which is freely moving, is going to make the entire structure negative. Therefore, N-type semiconductor is one in which the majority charge carriers are electrons. All right, so as many phosphorus atoms as possible will leave at least 1 electron each, making the entire structure negatively charged, okay, or having more negative charge carriers than positive charge carriers. Okay, so in an exam which has, let's say, 4 marks, asking you to explain how an N-type extrinsic semiconductor is made, you have to say these points. Okay, so you say, maybe they will ask you if the aid of well-labeled diagram, so you draw this diagram very well and then explain. So when a group 5 impurity, such as phosphorus, you can mention, is added, 4 of its 5 electrons participate in the bonding, but only 1 electron has no place to form a bond. By saying that, you have 1 mark. Already you have 1 mark for the diagram. Okay, so you have 2 marks altogether. The remaining electron is thus donated for electrical conductivity, and this makes the semiconductor negative. Hence, the N-type semiconductor is formed. Okay, so that's how you can get the 4 marks for a question that says, explain how an N-type extrinsic semiconductor is made. Okay, I hope you are good there on the formation of an N-type extrinsic semiconductor. In case you don't get it, please say so in the comment section. I'll be happy to come back to you and explain further. I don't mind even making another video just to clarify that point. But you can also contact us on the number shown in the home screen, where you can express your concern over failure to understand, and we should be able to assist you accordingly. My name is Mr. Paul Shilola once again. Please like, subscribe, and hit the notification bell so that you don't miss any lessons as they are uploaded to this channel. All right. Now, having explained the formation of an N-type semiconductor, extrinsic semiconductor, let's look at how a P-type semiconductor, extrinsic semiconductor, is made or is formed. All right, we mentioned that an N-type semiconductor is made by doping a pure semiconductor such as silicon or germanium using a pentavalent atom such as the phosphorus. Okay, now in order to make a P-type extrinsic semiconductor, you dope a pure semiconductor, which is a group 4 element, silicon or germanium, with a trivalent atom. Remember, tri means 3, so we are looking at any group 3 atom, group 3 element. If you go to your periodic table, you find that in group 3, the elements such as boron, gallium, and indium. Okay, so from the first 20 elements, you only have boron, but if you get an extended version of the periodic table, you find there's gallium, and indium. All right, so we are saying that in order to make a P-type extrinsic semiconductor, all you have to do is add these small impurities of group number 3 elements, any one of them, not all of them together, but just one of them, okay, depending on your desire. All right, so a pure semiconductor such as silicon has 4 electrons available for formation of a covalent bond with 4 neighboring atoms. Silicon, by virtue of its position in the periodic table group number 4, it means it's capable of making 4 bonds. You have 1, 2, 3, 4. 1, 2, 3, 4, and so on. Okay, so when you look at the group 3 elements such as boron, a group 3 impurity such as boron has only 3 electrons available for bond formation. If you look at boron, it has 1, 2, 3. These are, by the way, outermost electrons. All right. So when you bring the boron into the structure, you actually appreciate that only all the 3 electrons will be bonded. Okay, but it will happen that its neighbor, the neighboring silicon atom, in this case this one here, will be the only one with an electron which is not bonded, closer to boron. All right. So when boron fits in the silicon crystal lattice, it will have 1 electron less to complete the bonding, leaving a hole. So there's a hole there that is created. This hole means boron has not been able to donate to share an electron with silicon. Only silicon will be able to share its electron to contribute its bonding electron to boron, but boron will not have an electron in return. So that leaves a hole. Remember, this is a hole is a positively charged. It's a positive charge carrier. Okay. So since a trivalent atom, boron in this case, creates a hole that accepts an electron, boron is referred to as an acceptor atom. So here, boron is an acceptor atom because it has failed to donate to provide a bonding electron, but is accepting an electron from silicon, which creates a hole, a positive charge carrier. So the resulting semiconductor is called p-type. All right, the p-type semiconductor. The P stands for positive charge carrier. Remember that holes are by nature positive. So most of the charge carriers in this structure will therefore be holes rather than electrons. So therefore, p-type semiconductor is one in which majority carriers, charge carriers, are holes, which are by nature positively charged. All right, so we've discussed the 2 types of semiconductors. Namely, we have intrinsic semiconductors, which are pure examples of silicon and germanium, and their conductivity can be enhanced by simply heating them. All right. Remember, the effect of heat is to increase the kinetic energy of the electrons, enabling them to jump from the valence band through the small forbidden gap to the conduction band. All right, that's called intrinsic semiconductors. Other than that, we have extrinsic semiconductors, which are impure semiconductors made by adding some small impurities such as group 5 atoms or group 3 atoms. Okay, and the extrinsic semiconductors, we have just said that can be N type or P type, and in this video we have explained how each type of semiconductor can be made. Try to scribble some notes on what you have understood from this lesson, and then probably share with me on the number that has been shown there. Alright, so we meet again next time with our third lesson, in which we are going to look at more details of p-type and the n-type semiconductors by looking at what is known as a p-n junction diode. So thank you very much for being there. Without you we don't exist. It is because of you that we are here, and we wish you all the best, especially when you are getting closer to your exams. May you take your exams and studies very seriously and pass very well, especially in the sciences. We want you to do well in the sciences just as much as it is important for you to do well in the other subjects. My name once again is Mr. Pochilola. We meet you in the next lesson. Bye for now.